Uh, well, let's move to discrete, bosonic, quantum fields, big name. So we were going to, the name of the game now is to construct the path integral, understand it, interpret it exactly, not semi-classically, the exact one, but in Fock space. So let's introduce the whole machinery. I will start with the kinematics of Fock space. So, meaning the space, the basis, the operators, this kind of thing. Now I will, everything I'm saying you know already, okay? But let's go through it and let's notation and let's clarify the things that I need for this, to do the semi-classics later. So what I'm describing is, so I'm describing a system of n degrees of freedom, but specifically now this will be, these degrees of freedom will be my particles. I have n particles here. Let me make it very explicit, particles. And they are bosons. First keyword. And this, so you have a bunch of particles. I'm telling you they are bosons. Then you know that the quantum mechanical states have certain property under permutation of indexes of the particles. And the way to, I can make a huge detour into how to go from symmetrizing the wave function and end up with this occupation representation. I will kind of motivate it directly. The way to describe this type of system starts from specifying which single particle states my bosons can occupy. So if you want a picture, which is not my favorite, but imagine that you have a potential like that. And this potential then admits, forget about tunneling here and all that. Think about that each of these wells can be, defines some states there. Of course, the states get higher and higher energy and get very messy, but consider a system of wells and the low-lying states of these wells. So let's say, and let's do the extreme case, which can be tuned experimentally and all that, where actually I only care about one. For some reason, for example, I devised my experimental setup in a way that the next state in this well is here, and this energy difference is so large that to put a particle there it requires a lot of energy, and it's easier to put here or there, or to put two there and one there. So this kind of setup, and now the picture is ugly. Let's do it again. Then I have a state here, and a state here. These are single particle states. There is nothing mysterious, bosons, quantum field theory, nothing. This is a single particle problem in which I will do things, organize things in a way that to populate states with larger energy here takes a lot of energy, so I don't see them. I will neglect them. Okay, now, I will call this phi1, phi2, phi3, and so on. These phis refer to quantum mechanical states of the single particle problem. Well, now what we can do is I can put a particle there. I can put one particle there. And the quantum mechanical state of one particle, and these guys are called orbitals, by the way. I will refer to, it's a bad name coming from chemistry, but it's the kind of, we call it single particle orbitals, or simply orbitals. This state I have here, well, it's a state of one particle. I have one particle in the orbital 1. Perfect. I can also put the particle here or there. These are all states of one particle. But there is, I can consider the case when I have one or two particles there. They will interact, most likely, and one here. And the particles, I will call it the particle alpha, beta, and gamma. Well, that's the postulates of quantum mechanics tell us that a possible quantum state, let's take the particles for the second to be non-interacting. So this state will look like the particle alpha in the orbital 1 times the particle beta in the orbital 1 times the particle gamma in the orbital 3. And the postulates of quantum mechanics tell you, hey, if you have a system with several degrees of freedom, the Hilbert space you build out of the product of the states. And now there is the thing that with this representation, of course, this state is different from this state. This was exactly what I didn't want to do. Sorry. Let's do alpha 1 cross, then I put. No. No, there is nothing there. I have alpha and beta here and gamma there. Now, these two states are different because if you color the particles in different colors, you will see this is alpha, beta, gamma, and now I have alpha, gamma, and beta over there. These are different states, no doubt. But now, as we know, there is this property of the particles being bosonic or fermionic. And the cute thing about bosonic particles is that we make these two states, we identify these two states. The two states represent the same physical situation. And then, well, the proper machinery to do that goes into saying that a physical state of the system is actually a superposition of these objects where I kind of interchange my particles. And, but this takes, you have to start symmetrizing. It takes a lot of effort to do that description. There is a more economical description, which is the one we are going to introduce. Now, this is kind of first quantization description. The field theoretical approach starts with the concept of occupations. So what is the idea? Let's take an extreme case. Alpha, beta, with both alpha and beta are occupying the same phi1 single particle state. Alpha, beta like that, or alpha, beta like that, beta, alpha. Since the particles are indistinguishable, this has to be exactly the same state. So at the end, actually, I don't care. I don't care if I call this alpha or beta. All I care is I have two particles there. So the Hilbert space of a bosonic system of n particles, I would call it, which are indistinguishable, is called the Fock state, the Fock space, and I call it bosonic. I will talk about fermions tomorrow a little bit, but let's focus with bosons. This I will call the Fock, the bosonic. The Fock state is kind of bigger than that, but let me stay there for a second. I will call this a space of indistinguishable bosonic particles, the Fock space, and okay, it's a Hilbert space. Okay, you have two states, or the two elements of the bosonic Fock space represent two states, two physical states of the system, and I can add them. There is a scalar product, all that. It's a perfectly nice Hilbert space. Has a little bit more structure, but it's a Hilbert space. And then, what is the basis? A basis of this guy is, and I will introduce the basis now. Look what I'm going to do. For each of the single particle states, now, this is a nice picture because actually they do this in experiments, okay? The cold atoms people, they take a laser like that, create a standing pattern, and they put cold atoms in there. And the cold atoms are, you do things right, are bosonic, and they create these states all the time, putting cold atoms in optical lattice. And how do we specify the state? I will tell you. Okay, what I wanted to say is that this picture is nice, it's very visual, but please don't get attached to think that the single particle orbitals are kind of labeled by positions. You can think about this as well. You have take a single well with many states, blah, 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 many states, and you call this phi 1, phi 2, phi 3, and so on. That's a perfectly, also, the machinery works exactly the same, but this is no longer something that you populate in a space, but you populate more like in energy. But this is the machinery is exactly the same. So don't get attached to this. It's not the only possibility. So to specify states in this space, I will specify the number of particles in the single particle orbital phi 1, the number of particles in 2, and just to make things kind of, eventually we can make things infinite, but I will assume that I have D. I want to be careful with use the same notation as in the paper. D. I have D single particles orbital up to D, up to the number of particles in D. And since the number of particles, the total number of particles is fixed, I'm assuming that the total number of particles is given by this. Okay, now, to justify my claim that this state with all possible occupations, these are positive integers, of course, each of these n alpha is 0, 1, 2, as large as you want, of course, but you cannot go beyond the total number of particles. But they can be whatever. You can, as long as the total number of particles is respected, you can put whatever you want in there. Now, these states look very classical, you know. I mean, well, it's very easy to imagine what is. I just put n1 particles here, n2 here, n3. There is nothing strange, or there is nothing interfering there. Or they look very, very intuitive. It's the same way you will label states in the classical problem. How do you label your classical state? How many particles here and here and there? Where is the quantum mechanics? At this point in the orbitals, these are quantum mechanical states, I know. But the concept of occupation, well, is very, very classical. Okay, now, to support my claim that these states are a basis of the Fock state, well, this is something you have to go and prove. You have to take your system of bosons, apply your symmetrization operator, construct all possible states, and show that any state of the system can be described as a coherent superposition of these things. That's not trivial, but is in the mapping between symmetrization arguments and occupations is done in any book on many-body theory. Classic, all one. Fetter and Baleka, fantastic. I recommend. Where this mapping is done. For the time being, this is something you will have to believe, that actually this is a basis of the Hilbert space of the system. What does it mean? That an arbitrary state, whatever, is a coherent superposition over all possible sets of occupations. So I will label this with an n vector. This n vector is n1, n2, n3. Some coefficients, n. And I won't write this all the time, but please keep in mind that the total number of particles is fixed. If you are a quantum optics person, you don't care about that, because photons, you can have zero chemical potential. You can put photons, remove photons, no problem. But I'm mainly interested in describing cold atom systems. And in cold atom systems, there is a very fundamental rule telling you that you cannot make coherent superpositions of states of massive bosons with total different number of particles. So the state of two bosons here, one boson there. This is a two-particle state, this is a one-particle state. The superposition of these two cannot be prepared. It's not a physical state. But what I can do is to put two particles there and make the superposition with two particles there. No problem, this I can do. But the total number of particles has to be fixed. So in everything I'm doing and I'm assuming that, I won't write it anymore. I will write it just this one time. I will put, I don't know, let's call it n, which means I have this restriction always.
It's not the case of the superpairs, for example. They are bosons, and actually conducting state is a superposition of different number of superpairs.
Yes, but it's not the BCS state is not a physical state. Actually, to do things by the book, you have to take BCS and project on fixed total number of particles. And there are people doing that.
Yes,
It's an important. And the same, in cold atoms, we like to, many people like to think in terms of coherent states. Well, coherent states of cold is not a physical state. You have to project in total number of particles fixed. Please. Okay. Mm-hmm. Yeah. So, but in the I will be happy to. This is an important question, so I will be happy. My claim is that the BCS state, also understood as a system of fermions, is more related with a coherent state. And that's why we love it, because it's a coherent state. It's kind of condensate or something, very nice, but it doesn't, it allows the number of particles to fluctuate. And this is an approximation, but I will be happy to go on discussing this. I'm not the super expert in superconductivity neither. Okay, this is my Hilbert space now. The space of states is made of linear superpositions of occupation states. And so this is very important here. I'm saying this for the young people here. And this is a little detour, but I want to do it. Look, in this space, these are single particle orbitals. So I can construct things like this. I can do that. This is a rotation in the single particle Hilbert space. This is a perfectly well-defined quantum mechanical state. This is a phi plus minus. But please never confuse this. I can populate this state. I can construct the state of putting n particles in the plus minus single particle orbital. How do these particles look like? Well, they are delocalized here because phi plus minus is a superposition of these two. The particle is not here, not there. It's in a superposition of these two. This we do all the time. That's a Schrödinger cat. We populate the states which are given by superpositions of other states. That's okay. This is not one particle in one particle in two. One thing is this state. I put one particle here and one particle there. And another thing is, I don't even know how to draw it. I have this state. This is now a single state, and I put one particle in that single state, and I have another state which is with minus, like that, and I can populate that too. These are different things, and it's very important that you remember that, okay? This has led to awful confusions for me, at least, and for my students. So, okay, this was a little, and now you can think well, it's very, I mean, these states look very quantum. I put a bunch of particles here and there, but superpositions, well, that's kind of cute, right? I mean, what I'm saying is that this state that this is a physical state. The quantum superposition of these two things is a physical state. This is quantum mechanics in action. Those particles are not there or there. They are in these two particles are in the same orbital, but in different orbitals, the two together. And this is a perfectly valid Fock state. This is 2, 0, plus 0, 2. And all these monsters are here, and you can create them. Of course, from among all these monsters, if you have only one particle, if n is equal to 1, then you have one particle here or there, and all possible superpositions. That's fine. That's the one particle case. But in two particles, you start getting more and more possibilities, and things get a little bit more complex, let's say. But I like this state because they are very, very intuitive. And the experimentally, just say that, I populate this and this and this and that. Just like that, and you have the physical picture of the state that you have. Superpositions, where you have to then use your quantum mechanics to imagine them or to accept that these are possible states. Okay, enough with that. That's my Hilbert space. That's my basis. Operators. How do I define operators here? The funny thing is that to define operators in this space, I will take you out of this space, which kind of sucks. But I will introduce some operators that are extremely useful, but they are not observables, okay? They are not even Hermitian. They are called creation and annihilation operators. So I will introduce this guy that when it acts, let's say in N1, then here somewhere I have N alpha minus 1, N alpha plus 1, N D. I will call it, you know this from the harmonic oscillator, right? You know this, but look, I'm doing harmonic oscillators without harmonic oscillators. I'm just using kind of the algebraic properties of the harmonic oscillator. So this thing is defined to do the following, and I always forget where is the n, okay. This guy is doing the following, taking out the alpha occupation and adding 1 to it. But this is bad news, because this means that this thing takes you from the Fock space of n particles to the Fock space of n minus 1 particle. So to do this mathematically correct, we put together all Fock spaces to all possible number of particles and define these operators there. But we have a problem. This space is now too large, contains states that are not physical. So eventually we have to come back again to n particles, but we will do that, okay? It's wrong in the paper. And it's very elementary. Thank you, thank you. Oh, damn it. Okay, okay. Oh, that's shame on me. Okay, thanks for that. I always forget this. So this is called creation operator. I have the annihilation operator, just B. And I will only write what we need. And this goes in alpha minus 1, like that. They are postulate to commute, because these are bosons. And here is where things start getting crazy. For fermions, they anti-commute. They don't commute, but anti-commute. But for bosons, sorry, for different orbitals. Let me write it. I hope I'm doing the, I have it the other way around, but it can be that now I have a minus wrong. So these things commute if the orbitals are the same. What does it mean? Physically, if you put one boson in one well, and there's another mistake. No, okay, thank you. No, and it's correct in the paper. Thank you. Okay, yeah. And so these are, it's funny because I will, when you are doing standard quantum mechanics in orbital degrees of freedom, you start with Q and P, and the algebra of Q and P, the commutator, and then everything follows. And Q and P are physical. The position of the particle, the momentum of the particle, I can measure them, all that. Well, here the whole formula relies on this object, but these objects are not observables. And so that's what I say, operators. I'm not stealing observables. Let's start introducing the observables of the theory. I know this is a little bit boring. I know that you know this. We have to go through. So the most famous one is this. And it's called the number operator. I won't go into details, but this is elementary to show. The Fock states are common eigen states of the number operators. So this thing creates a particle, this thing destroys, this thing just reads how many particles are in certain place. They all commute with each other, you see. Can be shown explicitly. So this is, of course, an important observable. How many particles are here and there? So it's an observable, I can measure it. And how to measure it? Well, that's not a story, but these things can be measured. What else? This is not enough to construct all possible observables in this type of systems. And I will restrict to two important types of observables. Something that is called a one body observable. Like this. This guy is a one body observable. They have the following form. I would call it O. They have the following form. Sorry. So one body observables are a particular type of one body operators. A one body operator is this, but you demand has to be Hermitian. Why do we call them one body observable? And now we will start kind of having a picture of things here. Well, you can think that what is this guy doing to a state? It kills something, kills one particle in certain place, so kills one particle in the beta single particle state and put it in alpha. And this guy is doing that in many, many possible ways, given by these prefactors here, these amplitudes. So it literally takes one guy here and put it there, which is the physical process that you expect to happen when you put these systems under the dynamics. The particles are moving from here to there. You don't care which particle. You only care one from here, I put it over there. That's all you care. So one body observables are, if you, well, okay, that's it. And let's introduce right away the two body. Which is uglier. I would call it U. Is guess what? Really a monster. Some coefficients here, V, with 4 indexes. And now you kill two things and create two things. Sorry. Damn it. 2 indexes. I'm sure you know what I mean, but let's write it. I create two things and destroy two things. Okay, what is the effect of an external potential in a system? To change the state of your particles. So this is what this guy is doing. So this is the external potential is doing this. The kinetic energy is doing this. Just changing the state of one particle at a time. What is a two-body observable doing? Take two particles and change their states. What is this? An interaction. So these are the interactions. And now you can go on, because as Barbara knows, that nuclear background in nuclear physics, you may have three-body interactions. They are not, they are, how to say, they are way nastier, and also you use them when you need them, okay? Usually we stick to two-body interactions. In cold atoms, you almost always only use two-body. But you can also think I have three particles, they hit each other, and they go into different states. That's a three-body interaction. Of course, two-body interactions produce three-body interactions, but there are pieces of three-body interactions that are irreducible to three-body. And, but therefore, you can go on. Of course, you want this to be Hermitian. Please. Yes. The interactions are examples of two-body observables. Yeah, then a three-body interaction will be a three-body observable. Yeah, you just count how many of those you have, and that's it. And the physical interpretation is clear, no? I take three guys and put them to interact together, and the three of them change their states. So you destroy three, create three. But we will stop right here. Good. Observable. Okay. So what about the Hamiltonian? So what about dynamics? So this is all kinematics. These are the observables, these are the states. I can select a basis and take my Fock basis, represent these observables, diagonalize him, analyze the spectrum, all that. But of course, there is a special one, which is the Hamiltonian. I like to think that you postulate this, okay? But of course you have, if you know something about the single particle dynamics, you can kind of start building the many-body, the bosonic Hamiltonian. But think about this as something you postulate. The Hamiltonian in these systems have the following form. Typically, it has a single particle part, a one-body part, and probably you do Hermitian conjugate to make it a Hermitian, which imposes some condition on this H, doesn't matter. And it has an interaction part that usually you write as I did there. Some V, and then a bunch of beta, gamma, B delta, and Hermitian conjugate to make a Hermitian. Now, my first claim is the following. Sorry, I need to introduce the N. Sorry. An important observable is, of course, the total number of particles. Of course. Now, claim this Hamiltonian has common eigenstates with the total number of particles. This can be shown, okay? And what is the idea? Well, it's kill one, create one. Kill two, create two. The total number is the same. It's that simple. But it's good to use the algebraic properties of these operators and this definition of N to actually explicitly show that. It's a standard example, standard exercise. Okay. Well, why the Hamiltonian is important? Because with the Hamiltonian, guess what? I can calculate the time evolution operator. So what is the time evolution operator? I will assume that this thing is independent on time, this thing is independent on time. I can put it the time dependent, okay? I can put a time dependence here, a time dependence there, and then the time evolution operator has to be expressed more carefully. But for time independent, let me do it here. The H dt is 0. Then, well, you know what it is. E to the minus I over H bar Hamiltonian times T. That's it. I mean, I'm doing quantum mechanics. So what do I need to do quantum mechanics? You have to tell me, what is the Hilbert space where you are? What is your basis? Which are your operators? And roll it. That's it. We are ready. Now, that this is doing physics, well, that's it's not like, this Hilbert space and this operator. Well, this is doing physics. This describes the dynamics of cold atoms in optical lattices. for example, and many, many other things. Okay, so our goal, guess what? We want to construct the propagator from an initial and final configuration in Fock space. So what is the most fundamental question here? I give you a bunch of an initial state with these occupations. The dynamics. Tell me the probability amplitude to find the system in this other set of occupations after a time t under this Hamiltonian. The same question. So this is perfectly well defined. It's a basis in my Hilbert space. This is this Hamiltonian set of occupations. And I'm assuming, I'm not writing, but I'm assuming the total number of particles here is the same total number of particles there. Why? Because if not, this is automatically 0, because these guys commute. And states with total different number of particles are orthogonal. So that's it. The goal now is to construct this guy. Hey, Barbara, how is it going? How long do I have? Okay, quarter past 1. Are you still there? Who is sleeping? Let's see. Martin was sleeping. No. He wasn't sleeping. I was making fun. He wasn't sleeping. Probably I would be sleeping, but Martin was paying attention. Okay, well that's the goal, and of course you can calculate this using operator methods. You know, I give you a Hamiltonian basis. You can diagonalize the Hamiltonian in this basis, and which is cool because you see it's a finite problem. It's not like, because the total number of particles is conserved, the dimension of the Hilbert space is finite. Let's stress this. The dimension is finite. It's not like quantum mechanics in systems with orbital degrees of freedom, where every operator is essentially an infinite matrix, infinite dimensional matrix. Here is finite, so you would say, well, that's not a big deal. I mean, it's a finite dimension, you create your matrix, diagonalize it. The thing is that the dimension is finite, but quite large. So it goes something like number of particles combinatorial d minus 1. So meaning the dimension grows exponentially. If you take large d, exponential growth, large n, exponential growth. And that's the problem with many body systems. The dimension of Hilbert space grows quick. So, and okay, you can do that. You can introduce several powerful techniques to diagonalize. We are going to focus on trying to do the semiclassical propagator to capture interference effects in Fock space. That's the plan. And it passes through construct. We will follow by the book what Martin did. I will construct a path integral and then take the saddle point, the stationary phase approximation. And I have to formulate certain questions there. How do you justify stationary phase approximation? What is H bar? What is the thing that you are making large to justify your approximations? And you have to try to understand which are the paths. I mean, what is a path here, please? Thank you. At the end, what I'm going to show is that the semiclassical approximation exists if the number of particles is large. So if the total number of particles is large, and you don't have like all the particles in one orbital, but you have kind of occupations which are all large and not too extremely different from each other, I will show that you are allowed to do a stationary phase approximation. Just wait a second. Did you get what I just say? So it will come. I will show that the relevant parameter is the number of particles under certain conditions. And so I will satisfy your question in a moment. Right now, I don't know. Does this thing have a semi-classical regime? Right now, I really don't know. I have to construct the path integral and start checking whether this regime exists, and I will do it. This is the plan. Please, sorry.
There's two numbers, the number of particles and the number of orbitals. So you need that the number of particles be much bigger than the number of orbitals.
Being conservative, yes. I need large occupations. Now, turns out, asymptotics is magical. Turns out that we push these things to regimes where I have one particle per well. So, and still the effects that we found are still there. So, but as you know, this is magical. I cannot, I mean, it happened, we are all happy, but we cannot justify it. But this happens all the time, right? That asymptotics give you good results in regimes they are completely unexpected, but you cannot claim that this is kind of written in stone, right? But yes, we were able to push this quite badly, I have to say. Okay, well, are there any questions up to here? I mean, this is a bunch of harmonic oscillators. I hope that the whole terminology and big names do not disturb you. I have a bunch of harmonic oscillators, and with a kind of special condition that this number n has to be fixed. And out of this, I'm constructing the whole thing. So if we are okay with that, then I will go into the path integral. So what's the problem? I mean, I guess you already identify what's the problem here. How do I do a path integral? I take the time evolution operator, I decompose it into little steps, and then I start inserting integrals over some basis, the position or the momentum basis, integrals. And at the end, I end up with a lot of integrals, and I call this a path integral. Well, my basis is discrete. So the best I can do, if I want to follow that program, would be for the path integral, well, a split time evolution operator, that's fine. And I will insert, well, my unit operators, but my unit operators look like that. These are sums. The basis I'm using to describe my focus space is discrete. These are sums, not integrals. So at the end, I will end up with, I don't know, a path sum, infinite number of continuous sums. This is not a path integral. Well, still you can do it, but we don't know how to do any approximation there, semi-classical approximation, because I need an integral. I need to do stationary phase approximation. And whatever the monster you get, it won't be a path integral. The people in QCD call this kind of representation I will tell you. But they are willing to deal with a continuum of discrete sums, whatever it is. So you see the problem, right? I don't have a way to follow the standard program there. I need a continuum basis here. But then you remember the harmonic oscillator. I will define some cute operators now. Who will tell me how do I define Q? It's a definition. Look, there is no Q here. That's all I have. Well, now I will define some guys. I will call it Q. Can you imagine how? Exact. With some normalization, which is kind of conventional, we took square root of 2. And I don't know if this is, yeah, it's like that. Now, I need to stress that this system doesn't have anything like momentum in position. How do you think about the momentum of position of this many particle system? These are properties of this, these are operators I can define there. Bad news, okay, good news, Hermitian, great. Bad news, they are not observables because you see, they change the total number of particles, not observable. So they are kind of abstract things I'm introducing with the hope that will solve my problem, and they do. This is what I can show. Both of them are Hermitian, and I'm very happy that Martin is not asking the question that I was expecting at this point, so I will come back to it later, or I will tell you, well, Hermitian in which space, right? These things go out of the focus space. So I have, they are Hermitian in the big focus space, not in the one I'm looking at. So they are in that sense bad news, but okay, they are Hermitian. Therefore, I can show the following. I will do it with Q. They have a set. They have a common set of eigenstates. They commute with each other. I can show that Q alpha commutes with Q beta. Hermitian, they have a real eigenvalues. Continuous, these Qs, each of these Qs goes from minus infinity to plus infinity, continuous basis. I guess you see where I'm going here. They look a lot like position and momentum that we are used to. They are the position and momentum of nothing. There is nothing I can assign position and momentum here. This is a completely abstract definition. And the most beautiful one that you can prove based on this definition, because that's the definition, that's all we have. Based on that, I can prove the following. Just one sec. Please, question? Yes, but it's not the orbital motion at all, no? No, I don't know, because no, I mean I can, everything here, everything I'm doing here is refer to a given set of orbitals, you see? So, so if I want to,
But then the tunneling dynamics that is contained in H,
yes, yes.
should be sort of momentum.
Yeah, that's, yeah, but, yes, but this is something I determine from the single particle structure. This is a single particle object. These things contain the tunneling dynamics, sure, and are expressed in this language as taking something here, there. In the first quantized one particle version of this, there is a particle moving there, and this is how I determine this amplitude, certainly. That's the thing. I mean, second quantization is tricky because it's very powerful, but it relies on a very, very good description at the single particle level. I need to know what's that. Otherwise, I cannot do physics with this. So in second quantization, you are assuming that you know everything about the single particle problem, and you just start occupying those states. So your tunneling dynamics is in there. And most likely, you use already a real space picture to calculate it, but all that goes into the little h. What is in top of that is the many body dynamics. What I'm doing. I don't know if this is satisfactory, but this is not really positional momentum at all, There is no orbital motion here. I mean, that's the problem with this picture, that you think, this has a position and I'm moving it to a different position. But the right picture is that this has an orbital and I'm moving into different orbital. For example, if you go back to this, I'm populating things here. Now, the single particle dynamics takes something from here to there. This doesn't happen in real space. You see, this happens in energy space. I'm not moving anything from here to there. I'm changing the energy of my orbital. So how to associate a momentum to that?
But you can think in terms of a Rick oscillator that is some coordinate that is more or less fluctuating inside the oscillator.
Yes, but I don't need that there. I just don't need it anymore. And the Qs, I assure you, the Qs and Ps are not positional momentum of anything. And we can discuss this a little bit more in detail, but these are not orbital degrees of freedom of anything. These are abstract quantities. By the way, quantum opticians love this thing. They are called quadratures, the X quadrature and the P quadrature. And they measure them that, and they have nothing to do with the momentum of the electromagnetic field or anything, nothing. These are some properties of the field, let's say. But, okay, I love this equation. Yeah, you know, it's not obvious, right? From this definition to end up there, not obvious, and take some effort. But we have something very cute here. We have a basis of a space which is larger than the space that I want to be, that looks a lot like position and momentum. And I can invert these relations to write the creation and annihilation operators in terms of the quadratures and plug it here. And what you get is a monster Hamiltonian that depends on these quadrature operators. But it's a monster. You see, you have, to begin with, these Hamiltonians are completely symmetric in the quadratures. So you have a Q to the 4, you have a P to the 4. So they are very, very ugly things. Nothing like P squared over 2m plus potential of Q. They don't look like that. But they look like some ugly polynomial in Q's and P's. But since we have a continuous basis, and we have this Hamiltonian depending on my operators, we know how to construct the path integral in quadratures. So let me move here. So guess what? Well, we will do what we do in quantum mechanics when we have an object in a basis that is, we don't know what to do with it. Well, we represent in another basis. So this object is defined by this. Okay? Now, this basis, this Q basis, is a complete basis. I can show that the Q is Hermitian, has a continuous spectrum on the reals, commute with the other Qs, and satisfy this overlap with momentum. Well, we will do what we always do. We will change representation, introduce these unit operators there. And this thing is known, again, only from the definition of Q and in terms of creation and iteration and the properties of the Fock basis, just occupations. I can show that this quantity I can calculate. Let me be careful with prefactors here. This thing, of course, factorizes because from the properties, from the definition of Q final, let me write it. This thing is by definition product over alpha from 1 to D of the little overlaps N final N alpha final Q alpha final. These are these. And meaning at the end, what I need is to know one of them. I need to know what is Qn with a single orbital because I construct this object with the product. Who will tell me what's this? It's a difficult thing to calculate, but you should know. Just go back to quantum mechanics. Oh, Juan Diego is introducing these quadratures and terrible. An eigenstate of the harmonic oscillator represented in coordinates is an Hermite polynomial. So you can actually show that explicitly. Without solving the Schrodinger equation for the harmonic oscillator, nothing. From the algebraic properties of these objects, this happens and it should. Otherwise, well, that would be quite a mess. Sorry, 2 to the n factorial. Nth Hermite polynomial of Q. Well, so I know what to put here. Now, it's very ugly. It's a product of these things that you have to put there. And we will handle this later. But I know what to put in there, and I know what to put in here. Fine. What's my problem now? This object. Right. Okay. Now, if I don't tell you that we are doing a bosonic field, blah, 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 well, you see that? Well, that's something that looks like a coordinate, something that looks like a coordinate, in the middle, some ugly Hamiltonian that depends on P and Q, the time evolution operator. Well, we know, we have done this. I don't need to think physically at the moment. This is, I know how to construct the path integral. I will divide, expand, introduce unit operators in quadratures. Forgot to write this, it's important. I insert all these guys, I use this a lot, it appears all the time. Now I have a cute question. Do you see something missing here? There is no H-bar. You see, that's a fact. And when we did this first, before we realized that the people in quantum optics do this all the time, we start with these definitions and we prove this and we prove the Hermite polynomial thing and we were, wow, man, that's so cool. No H-bar. There is no. And why is that? Because these are names I'm giving to some objects. This is not positioning momentum. It's some two operators that I define. Huh? And the fact that you don't have H-bar here will have a very strong implications later. Please. No, they are dimensionless. That's the thing. That's the thing. And one stupid way to think about the need of H-bar in when you go from classical to quantum is precisely that a piece of classical phase space has units of action. And then if you want to do something like a statistical mechanics, and you want to count states, classical states, you cannot count them unless you transform them into, you can only count numbers. And that's why you need an H bar to count, you see? But in this case, you don't. And this is a reminder that QMP are, of course, you can do something that I don't like, but you can do something like define these guys with a unit of length, and with this one with the corresponding H bar divided unit of length, H bar divided unit of length, meaning you give units of length and units of momentum to these guys. And then what happens is that here in front, you will get your unit of length times your unit of momentum. And then you say, okay, this is an action, I call it H bar, but for me, there is nothing here telling you to do that. Why the hell would you do that? There is nothing in this formalism, there is nothing in focus space demanding you to have an H bar at all. So we don't do it, and we will be happy with it. Okay. Now coming back to this monster here, well, we know how to do. We know what to do. Know how to construct the path integral here. We follow the rule, divide the time evolution, expand the little time evolutions, insert, use the QP overlap, come back, put everything together. Guess what? This guy will be given by path integral over the space of quadratures, both in Q quadrature and P quadrature. Remember, why do I have a vector here? I have a vector there because I have D quadratures here. So you should then realize that something happened here. Somehow, my number of degrees of freedom now is not the number of particles. You see that? This kind of disappeared. This is not there anymore. The relevant way to describe these systems is depends on the number of particles just in a constraint I put to these numbers. But it doesn't change the dimension of these numbers. So if I give you this monster and I tell you that this Q is Q1 till QD, because this is what it is. I have as many Qs as orbitals, not as particles. So even if you send the number of particles to infinity, if you keep the number of orbitals fixed, that's the number of degrees of freedom. So think about this. I can imagine this. I have a double well, just that. And I put particles here. In first quantization, the number of degrees of freedom here is the number of particles you put. And I want to make the number of particles going to infinity. That's quite a heavy problem, and they interact. Now, in this formalism, the number of degrees of freedom is 2 instead of infinite. So you see that what we are gaining with this description is that we are kind of exploiting the natural degrees of freedom of the system. They are not the particles anymore, they are the occupations. And I have few of them, unless you want to make the number of orbitals to infinity, and then we are in trouble again. But if you keep the number of orbitals finite, this is the theory to deal with large number of particles. And so this is the dimension of these two fellows. Yes. Yeah, sure. I mean, they do this all the time. They call it the Bose-Hobart dimer. Two orbitals. And now, just a quick technical detour for the experts. Is time independent, 2 degrees of freedom, constant number of particles, constant Hamiltonian, integrable. So this is a many-body system that displays phase transitions, all the mess, but I describe it with a system with 2 degrees of freedom. But you know about this, right? Because this lifting model and all these effective models in nuclear physics are low dimensional. And this is what happened. Our first quantization approach to this, it is just crazy. But I can do a lot of physics with only two sides, but sending the number of particles to infinity. It's fantastic, very cool. Okay, okay. I don't need this. Well, you tell me what I get. I get the integral in the space of quadratures, path integral. These guys at initial time are the initial quadratures. At final time are the final quadratures. No condition on the P part of the quadratures. And what I get here is, let's write it first as a, yes, let's see if I have a space. The integral 0 to t of what? Well, my action, the integral of the Lagrangian in Hamiltonian form. That's why it was very nice to have, imagine that you don't have the Lagrangian in Hamiltonian form. How the hell do you do the path integral? There is no way to do that. There is no, starting with this Hamiltonian, there is no way to construct the corresponding Lagrangian. You have to solve an equation, couple equations of third order. So you have to do Hamiltonian. You have to. There is no Lagrangian here. And what you have here is what you expect, P of S dot Q dot of S minus the classical, but I won't call it classical anymore. I will call it mean field. Why? Because I will show you that this is the mean field Hamiltonian. So think about as classical if you want. Mean field. That is a function of the Q quadratures, the P quadratures, and I integrate on S. Sorry about the mess, but I needed to finish this. And guess what is the mean field Hamiltonian? Because, of course, I have to tell you how to construct that. But we already have a recipe to construct the mean field Hamiltonian, or the classical Hamiltonian. Be careful. I'm not doing semiclassics. You see? Again, I'm claiming that there is a classical limit there, but I'm not claiming that it's useful for anything at the moment. That's very, no, H bar is here. Okay, no, great, thank you. Very important. Very important. There is an H bar because the time evolution operator has an H bar, but only hits the Hamiltonian. And while this part doesn't know about it. And that's why if I make H bar going to 0, this won't give me anything sensible. Because when I make H bar going to 0, this stays as it is, and I have to do a stationary phase only on this part, and this won't give me any equation of motion. So there you see that we have to rethink the semiclassics here, but is there any other question? Ask me. Is there a question? Sorry, let me, what if I just, because no, that's an important equation, so let me write it here down more nicely. This monster times e to the I integral 0 t Better? Okay, great. Okay, so what is this thing? Thing is, even before I do semiclassics, I have a classical limit. Well, makes sense to take a look, actually. How does it look? Now, there are some things that I went through kind of quick. For example, whether doesn't matter what I get here. This is actually, this action defines a classical system. And that's the amazingly beautiful things about path integrals. If you do a path integral for unitary evolution, I'm not talking about dissipative systems or a quantum system, closed, path integral, whatever you do, doesn't matter what you do. If you reach the form of the path integral, it will give you a Hamiltonian system. Very non-trivial statement, if you ask me. Could be that the classical limit is some ugly stuff with is not, doesn't preserve volumes, or is not symplectic, or the equations of motion look very ugly. No, if you do the path integral, whatever you get there will give you Hamiltonian dynamics. Non-trivial statement, but it's true. So this is a classical object depending on Q and P. How does it depend on Q and P? It's very cute. Remember, the quantum Hamiltonian is some function of Q and P, or some function of the B's. I hate this vector hat, but and B daggers, all of them. I can go from B and B dagger to Q and P to do this thing here. But in any case, sorry, this is a function of these guys. Okay. Now, how do I get the mean field Hamiltonian? The mean field Hamiltonian, I will write it as a function of something that I will call fields, psi alphas, sorry, psi's and psi's conjugated. Let me just write it, and then I specify more. You will get that this is the original quantum Hamiltonian, but instead of the B operators, you write these psi guys, and instead of the B daggers, you write psi conjugate. And to completely make the connection with Q and P, then psi alpha is a shorthand for Q plus IP divided square root of 2. Well, so I give you I'm putting under the carpet some stuff, okay? Ordering issues, but bear with me at the moment. I give you the original Hamiltonian. It depends on creation and annihilation operators. Depends in certain way. So I just kill the hat. You see, I kill the hat and I call them psi's. And the psi's are related with the quadratures like that. So of course the Hamiltonian in quadratures is like that. It's really an ugly monster. But in terms of psi's, it's very, very cute. So for example, the single particle part of the Hamiltonian, remember, H or a yeah, for the Hamiltonian that I wrote, remember, H was the one body part plus the two body part. And the one body part was this sum of alpha beta, H alpha beta, B dagger alpha B beta plus Hermitian conjugate. And let me focus on that for the moment, the one body. That's the quantum mechanical operator. The classical mean field one body object is sum over alpha beta, the same coefficients, but now psi alpha conjugate psi beta plus complex conjugate, and you identify psi alpha with this combination of quadratures. And that's your Hamiltonian. So it's, although you kind of need the quadratures to do all this, when you write down things, it's way better to use these field variables because everything looks way more compact and nice. Okay, I'm still not doing semiclassics, but let's explore classical dynamics here for a second. So I told you how to construct the classical, the object that you put here in the path integral in terms of the original Hamiltonian of the quantum system. And everything is quantum here, but this is the technical name for this, we call it the symbol. The action has two pieces, something that we call the symplectic term, PQ dot, and something else. This something else is the symbol of the Hamiltonian. Please. Uh-huh. Yes. Not the product, the commutator. Uh-huh. 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 Mm-hmm. Mm-hmm. Yes. And okay, spoiler. This is how I identify 1 over n as the effective h bar here. That's exactly what we are going to do. Okay, I wanted to explore a little bit this mean field object. So one thing that we can do is, okay, let's take a look on the classical equations of motion. I'm not doing semi-classic yet, but from extremizing this action, well, I can construct classical equations of motion. So I go and do the variation with respect to Q, the variation with respect to P. I get some equations, which is what you expect. So from the variation of R equals 0, I will get, guess what? Q, let's do it alpha. Q alpha dot is the H mean field with respect to P alpha. And this H mean field depends on all the Q's and all the P's. What about, of course, this one? So, yeah, okay, this has Hamilton's equations in quadrature space, fine. But if you work out these equations a little bit, this is very a trivial exercise, I recommend. These two equations can be put together into a single one, which is, sorry, I need an H bar here. Now I need to, because I think I don't have it here. Wait a second. So units, this is 1 over time. Okay, that's fine, yeah. Oh, that's okay. So let's see, 1 over time, energy, see, it's like that. I hope. No. Yes. No, energy is energy. No, the Hamiltonian has units. It's an energy, of course. The time has units. What Q and P don't have units. Okay. Now, if I organize these equations, and I can show that, but it will take a lot of algebra, but it's straightforward. Guess what I get? I like to call it okay, let's keep calling T. This is very compact, you see? Instead of Q and P, I work with size, and they get very, very compact equations. And just for a second, imagine for a second that this that, that I don't have interactions. Just for a second. Consider the Hamiltonian has only the one body term. So for one body Hamiltonian, this equation looks like this. Like that. Do you recognize it? The Schrödinger equation. So the classical limit of a bosonic theory is the Schrödinger equation. The thing is that we are used to think that the Schrödinger equation is quantum, but Horacio here will agree with me. The Schrödinger equation is not quantum, it's a wave equation. It's quantum when you put on top all the interpretational kinematics aspects of quantum mechanics. Otherwise, well, it's a linear equation, just a wave equation. So for non-interacting systems, the classical limit is given by the old and dirt Schrödinger equation. And now, if you let interactions to be there, this thing gets cubic terms from the interactions. And the equation that you get with interactions is so important and appears so in so many situations that we gave a name to it. We call it the nonlinear Schrödinger equation. And if you take the limit of the continuum, we call it the Gross-Pitaevsky equation. So that's very nice. And you have seen that. People in cold atoms, when they think about the most classical description, they write down the Gross-Pitaevsky equation. Why? Well, because it's the classical limit. That's the reason. This is how the mean field description, that the Gross-Pitaevsky equation is referred to as the mean field description of the system, emerges as classical limit rigorously. Is the classical limit of the theory. But if you ask a person doing cold atoms, will tell you, yes, but I can only use that when the number of particles is large. So this is our first indication that somehow if we want to do semi-classics, and we want a classical limit that means something for quantum mechanics, we need to consider large number of particles. And I will do that. I will try to explain how this happens, and then, I think I will finish with that tomorrow. That's okay. It's a lot of material. Okay, but you know most of what I was saying. But let's stop there let's keep tuned, because tomorrow we are going to justify that statement, meaning we were trying to make something here in a way that I get a number of particles here. And then, perfect, n to infinity, semi-classics, I will just write down the semi-classical propagator. I don't care, same equations, same solutions. The subject will look the same as what we know, and we are ready to use it. But okay, this we will finish tomorrow. Thank you very much for the patience, and I'm very happy to discuss now or later or during the week any question or comment that you have. Thank you. Yeah, I know. Yeah. I will use the tutorial to propose exercises and solve them in front of you, because otherwise it makes no much sense. But yeah, I'm counting with it. Sorry, what's the question? Mm-hmm.
As far as I know, you go back, you go to the integrate. I mean, you go to the, as the limit
Sure, but here h bar is not something that I send to 0. Here h bar is 10 to the minus blah, 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 joules, is the constant of nature. It's not the parameter that I'm making large to construct, to bridge to the classical limit. This will be the number of particles, certainly. And then there are different, you can do semi-classics by taking fixed number of particles and h bar to 0, and this is good filler. And we have been doing that for ages, and it's very, very powerful. We have done a lot. But you can also keep fixed h bar and send the number of particles large. The classical limit you get there is the classical limit of Hamilton equations for particles. The classical limit you get there are nonlinear wave equations for waves, for fields, because this is a quantum field theory. The classical limit has to be a classical field theory. And what you get over there are nonlinear wave equations, like the Gross-Pitagoric equation. Now, this is screaming for the following. What happens when n goes to infinity and h bar goes to 0? That's the holy grail, and we don't know. Actually, this is few that we know about. Horacio is good playing with these limits, but this is a very, very fundamental question. How do I mix h-bar semi-classics that tell me what happens at the level of the single particle orbitals with large n semi-classics that tell me what happens when I put many particles there? This is essentially an open question, very hard. But the many body quantum chaos people kind of work in that direction. But I don't know if this answers your question. I'm willing to discuss. No, I will be happy to go deeper into that, really, really. Thanks again.